Physical interpretation of the standard rate constant K0. It is simply a measurement of the kinetic facility of a redox couple. For example, if we have the electrode and the redox couple, is having an interfacial or the heterogeneous charge transfer at the surface. As the standard rate constant is a measure of the kinetic facility of a redox couple, so the value of this rate constant is a deciding factor for the heterogeneous kinetics. For example, if we have a large K value, for large K naught, the equilibrium will be achieved at short time scale. So this is the first condition. The second condition is the value of K naught is small. This condition will lead to the sluggish kinetics, and the equilibrium condition will be achieved in longer time. Third condition is very large rate constants that could be range from 1 to 10 centimeter per second. These largest measured rate constants are associated with simple electron transfer processes. It means that the simpler the electron transfer, larger is the value of the rate constant. The example of this kind of fast electron transfer is the reduction or oxidations of many aromatic hydrocarbons such as substituted anthracenes, pyrenes, and perilines. So the cations and anions of these kind of structures is the category of the very large standard rate constants. The structure of anthracene, perilene, and pyrene are given here. Their anion and cation radicals fall in the category of very fast standard rate constant. So here we need to remind a few things about the fast rate constants that are observed for the simple electron transfer processes, which also follow the processes involve only electron transfer and resolution, means the back transfer. And the third point is no significant alterations in the molecular forms or the redox species have been observed. Other examples of the fissile kinetics means the faster standard rate constant means the achievement of equilibrium condition at faster rate is the formation of amalgams. For example, formation of sodium amalgam from the sodium ion through electron transfer towards the mercury working as electrode or working electrode. Formation of cadmium amalgam, in which two electrons are transferred for the formation of this cadmium mercury amalgam. And the third is the mercury itself act as redox species and as well as mercury electrode. The sluggish kinetics involve the small values of standard rate constant that involve more complicated reactions involving significant molecular rearrangement upon electron transfer, such as reduction of molecular oxygen to hydrogen peroxide or water, or the reduction of molecular hydrogen to, that is, monomolecular, or the proton to molecular hydrogen. Here this one is the monoatomic molecule, or also known as nascent hydrogen, that is reduced to molecular hydrogen and diatomic molecule. For these kind of sluggish reactions, the value of rate constant that is around 10 to the power minus 9 centimeter per second have been recorded. Even for some cases it is less than this value. That is the value of standard rate constant for the sluggish reactions. So therefore the electrochemistry is deal with more than 10 orders of magnitude for fissile synthesis. It means that the electrochemistry requires the synthesis for the higher order rate constants that must be similar to the first rate constants. Here one thing is needed to be mentioned, that the value of backward and forward rate constants can be increased by applying the higher potentials. As this potential act as activation energy to carry out the electrochemical reactions or the electron transfer processes at higher rate.